So in the last section of Chapter 8, we introduce some applications in physics and engineering and science that have to do with what's called harmonic motion or damped motion. Also, these sines and cosines represent some waves, and you can combine waves together to get new, more interesting types of waves. So what we want to do over the course of a couple of videos is build models for simple harmonic motion and analyze it, and then we want to study what's called damped motion. So simple harmonic motion is something that basically it's just a sinusoidal function. For example, a spring, if there's no air resistance, and the spring is what's known in physics as a perfect spring, it's not going to lose energy due to like the spring compressing over and over again. It just sort of oscillates back and forth from its resting position according to a nice, perfect sine or cosine type function. So you can find the amplitude by measuring the distance from its highest point to its resting point, or from its resting point to its lowest point, or it's half the distance from its highest point to its resting point. Either way, you'll find the amplitude, and this is how we found amplitude back in Chapter 6 when we were doing those graphs. The period is how long it takes to go all the way from top to bottom back to top. Okay. And simple harmonic motion, okay, just has a special kind of vibration. And in physics, the way it arises, is acceleration is negatively proportional to displacement from rest. So in other words, in the spring scenario, here's how it works. You have a spring supporting a weight, and it's just sitting there and it's quite nice. If you pull it down, the spring exerts a force up, whereas if you push it up, the spring exerts a force down. And the force is proportional to the displacement distance, but with opposite sign. If you push up, it pushes down. If you pull down, it pushes up. And that's where you get force is a negative constant times displacement. However, force is just mass times acceleration. So up to this constant of mass, you just have acceleration is proportional to distance of displacement, but with a negative constant there. Okay. And you can then take that equation, and in calculus, you can use that to say, well, if the acceleration is proportional to displacement, what's the function that generates that? And in a course called differential equations, you'll learn it's got to be a sine or a cosine or a combination of sines and cosines. So simple harmonic motion is exactly this. It's just a sine or a cosine, okay? A gives me the amplitude, and omega helps give me the period. And we did this back in Chapter 6, and now you're just learning that anytime you have a situation where acceleration is proportional to distance, but with opposite SIGN sign, you end up with one of these types of motions. In addition to springs, vibrating strings obey this. If you pull a string up, the string pulls back down proportional to how far you've released it. And then as you release it, it's going to vibrate back and forth between these upper and lower resting things, giving a sinusoidal motion. Okay, so this formula for amplitude and period we learned back in Chapter 6, so hopefully you remember that. Frequency is just 1 over the period. So for example, if the period is 1/10 of a second, how many times does it vibrate? 10 times per second. It's just the reciprocal of the period. So instead of 2 pi over omega, the frequency is omega over 2 pi. Okay, frequency just says how many times per second do I vibrate, whereas period says how much time to get one vibration. They're just reciprocals of one another. So let's build an example. Okay, suppose you have an object attached to a spring, and you pull it 5 inches from rest position and then release it. Abstractly, we now know it's going to do perfect harmonic motion. It's going to be one of these sines or cosines. The time for oscillation is 3 seconds. It sounds like we weren't given an amplitude, but we were. We pulled it 5 inches down. It's then going to spring back and go up 5 centimeters before coming back down. the amplitude is going to be exactly how far we pulled it from rest. So the amplitude is 5, and the period was also given. So all we have to do is determine the coefficient A and omega. We would wonder why a cosine versus a sine, but observe, where did the object start? So if I consider rest to be 0, it started down here. And then it's going to go up, and then it's going to come back down. This is a negative cosine shape. So it's easiest to describe this using a cosine with a negative coefficient. So since the amplitude is 5 and the period is 3, okay, we use -5 for the A, because remember we wanted a negative cosine. And solving 2 pi over omega equals 3, we get omega is 2 pi over 3. And there we have it, -5 times the cosine of 2 pi over 3 times t. Now we can predict where this object is whenever we want. Okay, another example. Suppose that the displacement is given by the following function, 6 times the sine of 2t. What is the maximum displacement from rest? What is the time required for one oscillation? And what is the frequency? How many oscillations does it do in 1 unit of time, which is measured in seconds? So the maximum displacement is just the amplitude. Okay. The maximum displacement is just the amplitude, that's 6. The time required is the period, so that's 2 pi over omega, and omega was given to be 2, so it's pi seconds. What about the frequency? Well, the frequency is the reciprocal of the period, so since the period was pi, the frequency is 1 over pi, so about 1/3 oscillation per second. That's pretty slow motion. It takes 3 whole seconds to do 1 whole oscillation. And that's really all there is to say about simple harmonic motion. Okay, so we're going to stop this there, and in the next video we'll come and we'll learn about something called damped harmonic motion, which you can see is significantly more complicated.